For example, if we want to talk about the glass phosphor example, in the glass phosphor example, there are 2 rows, 3 columns, and this is a balanced data example. It's one where all sample sizes are 3. Okay, so attached, for example, to any ABIJ, so any fitted 2-factor interaction, is a margin of error, and let's make this, say, based on, say, 95% confidence limits. Of the form. Now we're going to take a t-value times a pooled s times the square root of something that's going to have a formula that comes out of that table, and for the interactions this is going to be I minus 1 j minus 1 over mij, and that means that we're going to take 2.179. This is the t-value. It's the upper 2.5 percent point of t with degrees of freedom that we used in module 20. That's number of data values minus number of groups. That's 18 minus 6. That's 12, just as we used in module 20, times the pooled S, which is about 8.3 microamps, times the square root of 2 minus 1 times 3 minus 1 over m, which is 3, times I, which is 2, times j, which is 3, and so I've got then 2.179 times 8.3 times the square root of 1/9, and this is about 6.0 microamps. And the point here is that if I take this margin of error and I apply it back to these numbers, the minus 2.22, the 1.11, and so on, margins of error of 6 for numbers that are no bigger than in magnitude than 2.22 indicate that that lack of parallelism is really down in the noise range. So the point here is that this margin of error implies that the ABIJs are in the noise range. That is, I'm in any real scenario, I'm never going to get ABIJs that are exactly 0. The point here is that the ABIJs are not only smaller in magnitude than the AIs and the BJs, but they are small enough compared to their natural measure of margin of error that I can't even be sure that they're not really essentially, that they're not really standing for something that's essentially zero. So there's no detectable lack of parallelism on the plot or on our in our data set here.